So today we're talking about the Arrhenius Rate Equation. Arrhenius, interesting guy, looking him up. He's lived quite a while ago. Let's get it right. Relates the rate constant K to the activation energy EA. So K we've met before, the rate constant. A is the Arrhenius constant, sometimes called the frequency number. Or the frequency factor. It's similar to the collision rate. It's usually a pretty big number, but it's a constant. That's all you need to know. EA, of course, is the activation energy. Just remember that because we borrowed this equation from the physics department, we have to remember to put our energies into joules, or joules per mole for activation energy. R we know is the gas constant, 8.31 gas constant joules per Kelvin per mole, and T of course is temperature in Kelvin. So yeah, we could do a little bit of do some sums on this. We could ask the question, what happens if I have a 10-degree rise in temperature? How would that affect rate? Well, K is what we're trying to work out. It's changing. A is a constant, so let's just ignore A. Let's work out the total of E to the minus EA over RT for two different temperatures. We'll go for activation energy of 50,000 kilojoules per mole there. Okie dokie. So if we've got say we do this reaction at 298 Kelvin, then that would become E to the minus 50,000 over 8.31 times 298, which is 1.21 times 10 to the minus 9. And if we do at 10 degrees, so we do it at 308 Kelvin, that's 35 degrees centigrade, of course. Then we get E to the minus 50,000 over 8.31 times 308, which is 2.38 times 10 to the minus 9. And if we look at the increase is 2.38 times 10 to the minus 9 over 1.21 times 10 to the minus 9, which is almost 2. So this is a good rule of thumb. 10-degree increase in temperature almost doubles the rate. Okay, let's take our Arrhenius now and do some maths. If you don't follow the maths, don't worry. Should probably add that this form of Arrhenius is given to you in the exam. You don't need to learn it, as is the new version that I'm going to work out for you now. If I take logs, now that's not an ordinary log. The log that we've been using for pH and all that jazz is log to the base 10. And you might think that working to a base of 10 was pretty normal in our world. 10 fingers, 10 toes, and numbers go up to 10 and so on. But mathematicians prefer to work in base E, where E is the exponential. What is the exponential? Well, it's just a number. It's Gonna sneeze. Oh, nearly sneezed. It's a number 2.18281828, something like that. It's an important number, and we'll come back to that in a moment, how we use it. But if I take logs of both sides, then log k, and that's ln, by the way, natural log. Look on your calculator. Next to the log button should be an ln button. So natural log of k is natural log of a, and then using the log rule, that would be minus natural log of e to the minus ea over rt is just minus ea over rt. Again, if you haven't done this in maths, then you'll just have to trust me. Now I can rearrange that. So to say natural log of k is ea over r times 1 over t plus log a. Again, they will give you this version of the Arrhenius Rate Equation in the exam as well, but they won't give you this one. You need to be able to change that into that. And the important thing about that, of course, is that we've now got a y. Yeah, it's a rubbish pen, isn't it? We've now got a y equals mx plus c form of the equation. So where's this going? Well, if I collect a load of data for a bunch of experiments and I calculate the temperature in Kelvin and I work out the rate constant, and we've done some work on the rate constant so far. So we get a whole bunch of different temperatures and a whole bunch of different rate constants. What I can do now is I can work out log k, and I can work out 1 over t, and then I can plot a graph of 1 over t against log k, which will look something like this. The gradient is negative. EA is always a positive number. You can't have a negative activation energy. It wouldn't be a bump in the way if it went down. So EA is positive, R is 8.31, so minus EA over R is always going to be a negative number. So we'll get a negative gradient, something like this. Doesn't necessarily go through the origin. So we'll get a bunch of points for log k against 1 over t. And then in the usual way, I can now work out the difference in log k over the difference in 1 over t and calculate the gradient. And the gradient will equal minus EA over R. Of course, R is just 8.31, so then we can use that to work out the value of the activation energy. Just remember, of course, activation energy units are joules per mole. If ever anyone was going to make a mistake in this topic, it would be right there.